So picking up where we left off last time, we were talking about attractive forces. We've talked about 3 forces. Dispersion forces, which everything that has electrons has, so everything. Dispersion forces is, of course, our weakest force. And then we've got a slightly stronger force that some things have, not everything. Dipole-dipole forces, so things that have a permanent dipole. Things that are polar molecules have dipole-dipole forces. And then within that subset of things, we also have hydrogen bonding. So polar molecules also have hydrogen bonding because they've got hydrogen bonded to fluorine, oxygen, or nitrogen, directly. And so those can also do hydrogen bonding. And that explains lots of the behavior of matter. And we talked about different types of solids, crystalline solids, amorphous solids, different types of crystalline solids, molecular, ionic, and atomic solids. And then within atomic solids, there were even further distinctions of non-bonding, covalent bonding, and metallic, I think, are the 3 categories, and some vague properties, some general properties of each of those in terms of like their melting point. And then we talked about evaporation and condensation, and now we're getting on to some of the energy considerations with things like melting and freezing and other phase changes. So the energetics, what's happening with the energy when we're doing melting and freezing? When you add ice to a drink, it cools the drink down. We know this. This is why we add ice to drinks, to cool our drinks down. And that's because melting is endothermic. So the act of absorbing, or the act of changing from a solid to a liquid, it's going from a low energy state to a higher energy state. It has to gain energy to make that jump, to change from a solid to a liquid. So it's an endothermic process. It's absorbing that energy from the drink that you've added it to. So your ice absorbs heat from the liquid and it cools down the drink. We are overcoming, when we're melting, some of the intermolecular forces. And I'm going to write IMF here. Again, that's not the International Monetary Fund, that's intermolecular forces. So we're overcoming some of the intermolecular forces because now we're able to have our molecules moving past each other, but they don't have enough energy to completely separate from each other yet. On the other hand, freezing, going from a liquid to a solid, is exothermic. It's losing energy, it's emitting energy in the process of cooling down. This is often unintuitive to people. If you think about it for a little bit, you can come up with the fact that freezing is exothermic, but usually people's gut instinct is that freezing, because it's getting colder, is endothermic, but in reality it's losing energy. So the way that your freezer works to turn water into ice is you're putting water into your freezer. Your freezer is colder than the water, so it loses some of that heat. The heat disperses into the freezer, and the compressor and all the other mechanical stuff that goes on in your freezer is constantly removing that heat from the freezer compartment so that your water freezes. So the water loses energy to freeze. When it's in its liquid state, it has enough energy for the molecules to move past and around each other. We need to take away some of that energy so that they don't have as much energy, and then they'll eventually lock into place. They no longer have energy to move past and around each other. All they can do is wiggle in place. Related to melting and freezing, we have a quantity called heat of fusion. So this delta H of fusion, FUS is short for fusion. This is the amount of heat required to melt 1 mole of a solid. We'll often see it written over to the right of a reaction. In this case, we're just showing that it's going from a solid to a liquid. All right, that's all that's changed. It's still H2O. And the exchange of heat that's associated with this is a positive 6.02 kilojoules. And secretly, this is per mole. So you are expected to know that it's per mole or per mole equivalent. So if we had coefficients of 2 on these, then it would be per 2 moles. So again, this per mole part usually omitted. And the sign here is positive because it's absorbing energy. The thing that we care about, the thing that we're focused on here is the water. Oftentimes we'll call that our system. So with respect to the system or concerning the water is gaining energy to become a liquid. The same amount of heat is involved when 1 mole of liquid water is frozen. So if we're moving in the opposite direction, right, liquid to a solid, now it's negative. It loses energy. To freeze. Has to lose that energy so that it will get locked into place in its solid state. Just generally, a negative delta H is exothermic, and a positive delta H is endothermic, or absorbing energy. We can use this delta H to calculate the energy that it takes to melt a given amount of a solid. So our delta H converts between moles and heat, which will have units of joules or kilojoules. So let's see an example of this. We want to calculate the amount of heat absorbed when a 25.4 gram ice cube melts at 0 degrees Celsius. The heat of fusion for water at, there should be a 0 here, at 0 Celsius is 6.02 kilojoules per mole. Usually the problem will specify a temperature. It's just so that in case somebody happens to know that there's different values for different temperatures, you know, they're not like, actually, it should be this value, right? So that's just, there we're covering our bases. All right, so we have 25.4 grams of ice, and we want to calculate an amount of heat. We're also given the heat of fusion, and it's 6.02 kilojoules per mole. You will not have to memorize any of these delta H values. You'll always be given them. If you're not given them, please raise your hand and ask if it's like on an exam, but you should always be given them. So we're starting with this 25.4 grams. Ice is H2O. the 6.02 kilojoules per mole tells us that we need moles in order to be able to find heat. So we're going to turn grams of water into moles of water, dividing by 18.015 grams per mole. And that'll give us the amount of moles of H2O that is in 25.4 grams of water. And then in our kilojoules per mole, the moles part is on the bottom. So we can multiply it. And then the moles will cancel, and we'll be left with kilojoules, since kilojoules is on top. So 25.4 divided by 18.015, multiply by 6.02. The amount of heat, 8.49 kilojoules. You probably don't remember the amount of heat that was exchanged in our calorimetry experiment, but for most of them it would have been in the like 800 to 1400 joules, I think is what you would have calculated for half this amount of water, or double this amount of water, sorry. So this is half the amount, and it's like 8 times, 7 times the amount of heat. There's a lot of heat that goes on with freezing and melting compared to just changing the temperature of the water by some degrees. We can think about the energy that's exchanged in evaporation and condensation as well, since those are also important phase changes. So evaporation is endothermic, gains energy to completely separate the molecules or completely overcome our intermolecular forces. So rather than just moving past each other, they now have enough energy to break free and go their own way and turn into a gas. If you had to guess, which is harder, to just go from being locked in place to moving past each other, or to go from moving past each other to completely separated? Any ideas? It's the second one. It's the evaporation. Evaporation is harder. We'll see that show up in the delta H value. It's much bigger, unless I'm completely misremembering. Okay, so evaporation, cool, because our bodies do that. We do that. We use evaporation for cooling. When sweat evaporates off of your body, it's below the boiling point. It's going to take actually more energy to get it to evaporate. So it absorbs heat from our bodies, and that gets carried off in the water molecules. So the water molecules are taking more than their fair share of the heat, and we don't mind because that cools us down. And if you have a breeze, that intensifies the cooling effect, because sometimes what will happen at the microscopic level, the particle level, is those water molecules might leave, hit something, and then come right back and land back on your skin and give you your heat back. If you've got a breeze going on, it's pulling those water molecules away before they can come back and give you your heat back. There's probably also some other stuff going on, like with vapor pressure and things like that. But in my mind, that's what's happening, and so that's why a breeze helps cool you down. If you have high humidity, we don't have that, right? We get a dry heat, thankfully. If you have high humidity, that's going to slow down evaporation, because there's already a lot of H2O in the air. So there's less space for those water molecules to get into the air, and so that's going to prevent you from cooling down. That's why 90 degrees Fahrenheit with 90% humidity is oppressive, versus 100 degrees with 30% humidity Doesn't feel so bad. It's still super hot, but you're not dying hot, especially if you can get in the shade and you've got a nice breeze. Condensation, the opposite process, is exothermic. So hot gas, like steam, releases a lot of energy when it condenses. And in the case of steam, and getting steam on you, it's releasing a ton of heat, and that's why part of why steam burns can cause so much damage is because of the amount of heat that they're dumping out compared to if you were just touching the hot water, like if it was boiling hot. You touch it for a little bit, you're probably going to be fine as long as you're not holding your hand in a boiling pot of water. This effect, this exothermic, the heat release from condensation, is also part of the reason why overnight temperatures don't drop as much when our humidity is high. There's a lot of relatively hot water in the air, and as the temperature drops, the relative humidity drops. Some of that water is going to condense out of the air, and when it does that and forms water drops, it's releasing a ton of heat out into the environment that helps keep the temperature up. So around here, since we've got really low relative humidity, just generally, we might see temperature swings of 30 or 40 degrees Fahrenheit versus a much more humid environment might only see 10 or 15 degrees Fahrenheit change in temperature overnight. For vaporization and condensation, we've got delta H vap, the vap being short for vaporization, turning into a gas. Again, this is the heat required for 1 mole of the liquid, and it's for vaporization instead of fusion, melting, freezing, etc. Our value for water is 40.7 kilojoules per mole versus the 6.02 kilojoules per mole we saw earlier for melting. So this is a much, much higher amount. This is like 6 2/3 times the amount of energy. And for vaporization, it's positive because energy is required to overcome the intermolecular forces. You have to add water to your pot of boiling water in order for it to keep boiling. On the other side of things, we have condensation. For condensation, it's negative. We need to lose energy for our molecules to get trapped by intermolecular forces. We need them to be moving slow enough, have less energy, just be slow enough for them to hit another molecule and get stuck and not be able to just break free again. We can also use the heat of vaporization to do calculations. It's the same as the condensation, or it's the same as the fusion and the melting. Okay, calculate the amount of heat in kilojoules required to vaporize 1.75 kilograms of water at its boiling point. The heat of vaporization is 40.7 kilojoules per mole. This would be the same as 1.75 liters. By the way, it's not important for the problem, just to give you an idea of how much water we're talking about boiling here. And I'll give you some time to try that one. All right, that was a small amount of time for you to give it a shot. Let's walk through the calculation. So just like our previous problem, we're starting with grams. In this case, we're starting with kilograms. So we'll want to turn kilograms into grams. There are 1,000 grams within a kilogram. So we've got 1,750 grams. And we can convert that to moles by dividing by the molar mass. That switches our grams into moles. And then we multiply by 40.7 kilojoules per mole. And our moles cancel, and we'll be left with kilojoules. So this is 3,954 kilojoules, or 3.95 times 10 to the 3 kilojoules, which is a lot of energy. It's also for basically half a gallon of water. Questions about signs? Delta H, freezing, melting, evaporation, condensation. Another possibly interesting aspect of all of this is seeing how big this value is for the heat of vaporization, the same value for condensation. If you're drinking ice water in a non-insulated glass and you get condensation on the outside, that condensation is a lot of energy being dumped into your nice ice water. So you're losing a lot of heat to that. If you then wipe away all that condensation, you're going to get more condensation. It's probably going to warm your water up, warm your drink up faster than if you just left the condensation there. Here's a bonus. This is kind of like the harder side of questions that we can do with this concept. We have a drop of water. It weighs 0.48 grams, and it condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If the heat released during condensation goes only towards heating the metal, what is the final temperature? So final temperature in Celsius of the metal block. We're given that the specific heat capacity of aluminum is 0.903 joules per gram degree Celsius, and we would also need some other information like delta H vap. Let's just assume that it's 40.7 kilojoules per mole. And we'll also need the C for water. So seawater is a mixture of water, salt, and fish excrement. Sorry, different seawater. Our seawater, 4.18 joules per gram degree Celsius. This is a problem that we have all the tools to solve. It's just that you have to put them all together. Actually, I don't think we need the seawater, which is great because that makes things easier. So we have a drop of water. It's 0.48 grams, and it condenses. So that means it's going through this delta H vap. It's using this delta H vap. So how much energy is that drop of water producing or releasing when it condenses? We can calculate that. Convert the grams to moles. So this is the number of moles after this calculation. This is the number of moles that's in that one little drop of water. 0.5 milliliter, very small drop of water. Or normal drop of water, I guess, because they're already small. And then 40.7 kilojoules per mole. Right, so this is the calculation that we've been doing. We're figuring out how much heat is released by this tiny little drop of water. So 0.48 divided by our molar mass times 40.7. So this drop of water is releasing 1.084 ... kilojoules, 1084.4 ... joules. Should the sign of this be positive or negative? Is the water gaining heat or is it losing heat? It's losing heat. So we would want to use the negative 40.7 kilojoules. In reality, as long as you can think through, should we have positive or negative values at some point, it doesn't really matter. But we're being diligent, so we're putting a negative. All of this heat goes towards what? The metal. The metal is gaining this heat. So what amount of heat, positive or negative, for the metal? The heat will be getting the positive value of this. So the metal is receiving 1084.4 joules. So that's an important piece of information. We've also got the mass of our block of aluminum, and we've got a specific heat capacity. Does anyone remember what equation we're using here? Yeah, we're going to be using Q equals mc delta T. So the Q value is this heat. The M value is this 55 grams. The specific heat capacity is the C. We are solving for delta T. So doing the algebra real quick, it will turn into delta T equals Q over MC. So our whole calculation turns into this. Units cancel out. Degrees Celsius flips to the top. So our change in temperature is 21.83 ... degrees Celsius. So our 55-gram block of aluminum, which is kind of small, is changing its temperature by almost 22 degrees Celsius. That's the difference between freezing temperature and room temperature, depending on what room you're in. So what is our final temperature of the metal? Yeah, something like 46.8 degrees. Our change in temperature is equal to T final minus T initial, or since we know that our temperature is going up, we can just rationally think about, well, we've got a change in temperature of 21.8 degrees. It's going up from our initial temperature, so we add it to our 25 degrees Celsius. If you use the negative J here, then you get a negative value for your delta C, or your change in temperature. You could probably, make that work in your head to figure out that you need to make it positive. So delta T plus Ti equals Tf, which is 47 degrees Celsius after we round. So this is on the more involved, the more complicated side of problems. I think I usually put one of these on exam 4. It's nice to have a fun question every now and then. Questions about any of the steps, the process? All right, we can plot temperature, that's our y-axis, so the temperature of a sample of water, and time on our x-axis. We can plot those against each other. We've got a sample of water that we're starting with ice at negative 30-ish degrees Celsius at A, and we're heating it. So we've got it, ice in a pot maybe, over a boiler or a burner, and over time its temperature is increasing. What states of matter do we have for each of these straight line segments? So we've got A to B, B to C, C to D, D to E, and E to F. What states of matter do we have moving from A to B? Solid, liquid, gas. We can have multiple. For A to B, we're below the freezing point, so we just have ice. When we are, so we're heating the ice, it says that there. When we're going from B to C, our temperature is flat. We're still adding heat in, but the temperature isn't changing. That means that we are at a phase change. And at a phase change, when our temperature is locked, we have two states of matter. I'm going to write, instead of ice, just solid. So we have solid and liquid at this state, or at this segment. So this B to C. As we're melting the ice, we still have some ice present, but we also have the liquid water present. When we've got two adjacent states of matter present in the same thing, we're locked in at the whatever temperature it melts at or freezes at, in this case. So we're locked and loaded there. And then once we get to C, our temperature starts going up. That means that all of our ice has melted. Remember what I said about ice water last class? If you're drinking ice water, it's a very consistent 0 degrees Celsius. Once your ice melts, it's the Wild West. Who knows what you're getting? So from this C to D, since our temperature is changing and we are in the temperature range that corresponds to liquid water, we've just got liquid water. And then we get to 100 degrees Celsius. That's our boiling point for water. And our temperature gets locked in again. So during this very long segment, all of our heat energy is going towards vaporizing the water. Since our temperature is locked in, even though we're adding heat, that means that we've got two states of matter. We're at a phase change, so we've got our liquid and our gas during this vaporizing water part. This is like just boiling water. So if you just leave your pot of boiling water on the stove long enough, eventually it'll all boil off, and hopefully you don't do that. And then we get to E, and all of our water has boiled off. So all the water is gone, the liquid water, and so from E to F, it would all be steam. which is the gas phase of water. Questions about any of that? We can also do calculations relating to these phase changes. So this would be another example. This is a little bit more involved than the previous example that we were looking at for something condensing. We have a 50-gram ice cube. It's at 0 degrees Celsius, convenient. And it's added to 500 milliliters of tea at 20 degrees Celsius. I don't know why our tea is room temperature. Once that tea and the ice cube have finished doing their thing, what's the temperature of the tea? We can assume that there's no heat transfer to the surroundings. The density of the water and the iced tea in this case is 1 gram per milliliter. And we've got various C values and the delta H fuse of water. So one important part of this problem, I could ask you, this would be, I would have little devil horns if I asked you this. I could ask you, what's the final temperature of the tea, just period? And I think that that would be a very devilish question to ask you. The question that we're being asked here is, what's the temperature of the tea when the ice has just finished melting? And those are two different problems, because one of them, we're just calculating how much energy is associated with the ice melting and how much energy is that stealing from the liquid water. The other one says we've got the ice that's melting and that turns into water. We've also got the water from the tea, and those temperatures have to come up and meet somewhere in the middle, and that requires a lot more algebra. I accidentally asked my 1A students last semester a question like that. One student got it correct, and part of the reason is that I would use one of these whole whiteboards to do the algebra for that. It's a lot more involved. The question that you're being asked here is not that crazy. So let's look at what we know. We've got a 50-gram ice cube. It's at 0 degrees Celsius. That's the melting point. So it doesn't have to heat up at all before it starts to melt. We also have 500 milliliters of tea at 20 degrees Celsius. We're looking for temperature of the tea right when we've finished melting. So let's figure out how much energy does it take to melt our ice cube. We've got 50 grams of water in our ice cube. Is this looking familiar? 18.015 grams per mole to figure out how many moles of ice we have in our ice cube. And our delta H for ice is 6.02 kilojoules per mole. So the amount of heat that it takes to melt that ice cube is 16.7 kilojoules. So 16.7 kilojoules to melt the ice cube. Where is the ice getting that energy from? The tea. Taken/absorbed from the tea. That means that the tea lost this same number of heat. So the tea loses 16.7 kilojoules. when it's melting the ice. So the Q of the T is negative 16.7 ... kilojoules. For unit's sake, I'm going to switch that over to joules. Functionally, this is almost the identical problem to the one that we did before with the water drop condensing onto the piece of metal. Stepwise, it's almost identical. One thing that's different is that we're given that we have 50 milliliters of T. The density of water, just generally, you can always assume this, almost always assume this, is 1 gram per milliliter. So we can also say that we've got 500 grams of T. It's an approximation, but that's our mass. We're going to be using that Q equals MC delta T thing again. Before we do that, do we have questions about how we got here so far? I realize it's a lot of steps. I'm kind of just sprinting through it. All right, back to running. So Q equals MC delta T. Our mass is 500 grams. Our C value is 4.184 joules per gram degrees Celsius, and we are looking for the change in temperature, the delta T. I'm going to skip some of the algebra stuff. So let's find our delta T. Our delta T is negative 7.986 ... degrees Celsius. The negative sign here meaning that our T cooled down, which makes sense. We added an ice cube to our T. Our T should have gotten colder, not hotter. So we can use delta T equals TF minus TI, or we can just think, okay, if the temperature went down, subtract basically 8 degrees Celsius from 20 degrees Celsius. (20.0 degrees Celsius minus it would be plus negative. I'm just going to write minus 7.986 ... degrees C. So the final temperature would be 12 degrees Celsius. Again, this is on the more involved, the more complicated, the harder side of questions that I would ask about this, and I would only expect to put one on the exam. Questions about the T? There's all sorts of fun experiments that you could do at home, calculating like what's the optimal amount of ice to add to my drink to make sure that it gets just down to freezing point without like getting overly watery or whatever. You could figure that out. If you've got like a go-to drink, you could probably calculate this is the amount of ice that I need to add, and then I'll know that it's at my preferred drinking temperature. And then you could invite people over and make them the drink with your special weighed out amount of ice, and you'd look really fancy and cool. They'd be like, wow, you really take this seriously. You'd be like, yeah, I took chemistry for this. All right, other stuff that's related, solutions. So this is also kind of in the realm of attractive forces, which is our chapter. Solutions are homogeneous mixtures. The homogeneous means like basically smooth consistency. Not chunky, not having separate layers, so think Pepsi. If your Pepsi has a chunky consistency or multiple layers to it, something's wrong with your Pepsi. Coffee would also be a solution. So it's a homogeneous mixture. A mixture has two or more substances in it. Solutions are all over the place. They're not just liquid solutions. There are also gas solutions. We're breathing, not drinking, a gas solution. The air that we breathe is a solution of gases mixed into other gases. The water that we drink is also a solution. It's not just pure water. There's little ions and things dissolved in it, probably some fluoride, a little bit of salt, a little bit of carbonate, other things like that. So for your definition, a solution is a homogeneous mixture, not a heterogeneous mixture. Here are some types of solutions and some examples of those. So these are like our strict definitions. It's two things that are mixed together, and it's a homogeneous mixture. We'll learn what solvent phase and solute phase mean shortly. But we've got mixture of gas in gas. That would be air, as an example. Gas in a liquid, the CO2, the bubbles in our drinks, would be an example of a solution that's gas dissolved in liquid. Liquid dissolved in liquid. Ethanol in water and alcoholic drinks. Solids can also dissolve in liquids like salt water. You can get gases that dissolve into solids. You can actually get H2 dissolved or absorbed by palladium metal. You can get liquids dissolved into solids, and you can also get solids dissolved into solids, things like bronze and other alloys, stainless steel. So there's lots of ways that we can make solutions. They're not all liquids and liquids. However, that is generally what we'll be talking about. Okay, so what are solvents and solutes? Our formal definitions for solvent and solute is the solvent is the majority component, and the solute is the minority component. So in any mixture, you're generally going to have one thing that is most of the mixture. That is the solvent. You'll also have one or more things that exist in smaller amounts, and that's our solute. These are our strict definitions. Generally, when we're talking about things, the solvent is the liquid. Since we'll often be talking about solids dissolved in liquids, we're generally going to talk about the liquid as being the solvent, even if it isn't strictly speaking the solvent. Even if it's somehow the minority component, usually what we mean is the liquid when we're saying solvent. So you could program in your brain solvent equals liquid. This will generally be true for you. Our most common type of solutions are those where water is the solvent, the majority component, or just the liquid that's dissolving things, and we call those aqueous solutions. You can also have other solvents that are used, especially if you have nonpolar solutes. You can use things like paint thinner, hexanes, dichloromethane, which I guess is polar. But there's lots of things that you can use other than water. And in a lab, not a general chemistry lab, but if you do organic or like you're working in a commercial lab, you will very often use things that are nonpolar solutes. We have a phrase, like dissolves like. Pretty much every chemist should hear this phrase and understand what it means, or should know what this phrase is. Most general chemistry students should also know this. Like dissolves like. The idea being that polar solvents dissolve polar solutes. So if you have a polar solute, an ionic compound, for example, and you are wanting to dissolve that into something, you will pick a polar solvent. That could be water, that could be ethanol, that could be methyl alcohol, methanol, it could be acetone. Anything that falls into the realm of polar solvents could be a good candidate for dissolving that. It could also be something that's not a salt. It also applies to the other side of the coin. Nonpolar solvents dissolve nonpolar solutes. So if you're trying to dissolve some nonpolar solutes, you might use hexane, you might use diethyl ether, you might use toluene, you might use xylenes. I think xylenes are nonpolar. Anyway, the basic idea is like being polar or nonpolar dissolves like polar or nonpolar. You're not going to dissolve a nonpolar compound into a polar liquid. The reason for this is that when we try to dissolve something into a solution, we get competing attractive forces, competing intermolecular forces. So what we're looking at on the screen here is some possible interactions. We've got water molecules, and we've got salt formula units, sodium chloride formula units. So we've dumped salt into a liquid, in this case it's water, and there are competing attractive forces. The water molecules have attractive forces between each other. They've got hydrogen bonding intermolecular forces. The sodium chloride formula units have intermolecular forces. They've got positive and negative charges that are keeping them together, generally. In order for us to pull apart the sodium and the chloride, we need to have stronger forces between our water molecules and our ions to actually pull them apart. If we don't have strong enough forces between our water and our ions, the ions will just stay together. They won't dissolve. So these forces need to be stronger than this force. And for sodium chloride, that is the case. Water has strong enough intermolecular forces with the ions that it can rip all of those ions apart up to a certain point. For other intermolecular or other ionic compounds, that's not the case. So calcium carbonate, for example, in calcium carbonate, the calcium and carbonate ions have such an affinity for each other that the water can't pull them apart. And so it doesn't dissolve, or at least doesn't dissolve very much. When a solid dissolves in water, like sodium chloride, this is what it looks like at the molecular level. So we go from having the sodium chloride chunk into having sodium chloride ions dissolved in solution, and they're surrounded by water molecules all around them. They're not existing just free-floating sodium and chloride. And the little partial negative sides of our water molecules match up with the sodium. The little partial positive side of the hydrogens in our very polar water molecules match up with the chloride ion. It just stabilizes the charges. So that's how they actually exist in solution. It's sort of like Buzz Lightyear in the claw machine with the little green men all around, save us, that sort of thing. Or outside of the claw machine also, because I think the LGMs really like Buzz Lightyear. This is basically the same thing, just showing that we'll often represent it just as the ions and omit the water part. You should know in your head. You should know in your head that there are water molecules around the ions. We're just kind of taking a shortcut, simplifying our graphics. I don't want to make graphics that have all of the H2O molecules around each of these ions. That's a big waste of time. I would rather waste my time other ways. A sodium chloride solution, NaClAq, does not contain any NaCl units. The aqueous part means that it's dissolved ions, aka, in other words, Na plus Cl minus. It actually exists as Na plus and Cl minus. It doesn't exist as NaCl units floating around together. The aqueous means that the ions have separated. So that means they're separated or dissolved. Substances that completely dissolve into their ions in solution are called strong electrolytes. Strong electrolytes completely dissolve or dissolve completely. The electrolytes part of this just means that they're ionic. The strong part is the part that means that they dissolve completely. Any guesses on what our other option for electrolytes is? If you're not first, you're last. If you're not strong, you're weak. So our other option for electrolytes would be weak electrolytes, but I guess that's not the next slide. So we're talking about ion dipole force instead. This is our fourthest force. Remember that we learned 3 other forces: dispersion, dipole-dipole, hydrogen bonding forces. We also have the ion dipole force. This is the force between, you guessed it, an ion and a dipole. So something that has a dipole, something that's polar, and an ion. The dipole has a partial positive or partial negative charge. It actually has both. The ion has a full positive or multiple positives or multiple negatives charge. And this is important in solutions of ionic compounds. In these examples of sodium and chloride dissolved in water, the dipole part is the water. The chloride part is the ion, for example. Question? For the ion dipole part, the ion is the chloride. The dipole comes from the water molecules. So in dipole-dipole forces, we've got forces between 2 things that have dipoles. Now we've got ions instead of one of our dipoles. Ions have full positive or full negative charges versus dipoles, which have partial positive or partial negative. If you had to guess, which is stronger, ion dipole or dipole-dipole? Ion dipole is much stronger. Ion dipole is stronger than dipole-dipole. Also hydrogen bonding, because we have a full positive or full negative charge. Ions also work on trains. So pure water does not conduct electricity. You may know that. You may have not known that. You and I have never in our lives encountered pure water, except maybe in like water vapor. But like you've never had in your hand a cup of pure water. There's always been some dissolved ions in it. Especially because we live around here, all of our water's hard. Even the bottled water has ions in it. Pure water tastes awful, or close to pure water tastes awful. If you've ever tried distilled water, it would taste like distilled water, but even worse. It's ions, actually, that do the conducting of electricity. So ions in a sodium chloride solution, a salt solution, conduct electricity. Electrolytes just generally conduct electricity. In solutions. So if you have strong electrolytes, those will conduct electricity very well because there's lots of ions in solution for the electricity to travel through. If you have something that doesn't form ions, like ethanol, ethanol is not made of ions. It doesn't conduct electricity very well. If you've got something that only partially produces electrolytes, like acetic acid or calcium carbonate, you're going to get low conductivity because of not having very much dissolved in solution. So electrolyte solutions contain dissolved ions. They conduct electricity. Non-electrolyte solutions contain dissolved molecules, which are neutral and don't conduct electricity. In theory, if you somehow got your hands on pure water, lots of pure water, you could fill a bathtub with it and take a bath in it, and you were perfectly clean and you didn't release any ions into the bathtub water, you could safely make toast in the bathtub. However, you do not have pure water, and so if the toaster falls into the bathtub will conduct electricity, and you will be toast, possibly. So don't make toast in the bathtub. You have to make your toast beforehand and bring it into the tub with you. Otherwise, you could get zapped. Last thing that I'll write here, strong electrolytes. Strong electrolyte solutions, rather. Conduct well. Weak electrolyte solutions do not conduct well. You can actually get very close to pure water, and I have been around that before. And one of the measures for seeing how pure your water that's often used is the resistance of water. It's got a really high resistance value. It costs a lot of money to get those sort of fancy, expensive mega ohm water systems. But that's one way that you can measure the ionic purity of your water. There might be non-electrolytes dissolved in there, but that's not all that important. Any last minute questions about this? Great.